Hey all, welcome to McGuire Physics. This is McGuire, and today we're going to be talking about solving free fall problems. Before we do that though, we have to define what free fall means. And generally, something is in free fall if gravity is the only force acting on it. So this is if you drop an object and you ignore the amount of air resistance on it at all. When you drop something like a balloon or a parachute or a coffee filter, there's going to be a lot of air resistance on that, so it is not in free fall. Generally, if you drop something circular or something that's overall pretty heavy, pretty dense, it's going to be considered free fall, which is all the problems we're going to be using in this class. So let's define that. Free fall. Free fall is a state in which an object is experiencing gravity and no other forces. A state in which an object is experiencing gravity and no other forces. The unique thing about objects in free fall is that they always accelerate at the same rate. So this is a number to memorize. Anything in free fall is going to have an acceleration of negative 9.8 meters per second squared. So what that means is that every second, the speed of a freely falling object will either increase or decrease by about 10 meters per second. Each second that passes, it'll do that. So that's pretty relevant to all these equations up here. Anything that has acceleration in it is going to be very useful to us because we can just plug in 9.8 to all of these. All of these can just be plugged as negative 9.8. The other thing about free fall problems is that these x's here are going to be written a little bit differently. If you drop something, it's going to fall in this manner. So instead of calling that change in x like we did yesterday, we're going to call this change in y. So just a little formality there. You don't always have to do this. It just comes up from here and there. So we're going to dive into an example here. We've got two examples to go through today. The first is about an object that's dropped. So that's example one. Example one. A rock is dropped from a height of 80 meters. How long does it take to reach the ground? A rock is dropped from a height of 80 meters. And the action statement is, how long does it take to reach the ground? How long does it take to reach the ground? So we'll start off with a picture. Now normally we draw our picture sideways, but since this is falling down, we're going to draw it going up and down. So we've got a rock, it falls to the ground here, and we're going to put an arrow at the bottom to represent that it's moving fastest at that location. We also have to label the positions. Now it starts up here, so I call that y initial as opposed to x initial, and it ends at a height of about 0. That's our y final. And we'll label this as change in y. So that gives us a nice visual of what's happening. The object starts up here with a velocity of 0. It drops all the way to the floor, and right before it hits the floor, it has some finite velocity. So we can figure everything out from there. Asking us for time, so I'll label it as such. As we said, the initial is going to be 0. since it's dropped. If you hold something in your hand and just grip it tightly, it's going to have a velocity of 0. Right when you remove your hand, it's still going to have a velocity of 0 for a split second. Just after you let go, it starts to speed up. So that final velocity at the bottom there is unknown. We could calculate it, but we might not need to at all. Our change in y is going to be negative 80 meters. You might be wondering why the negative is there. Generally, if you have an object that moves downward, it's going to have a negative displacement because it goes from a positive position to a negative position. So it drops quite a bit. The displacement is negative. And finally, the only new thing from today is this portion. I'll put it in red. A is negative 9.8 meters per second squared. 0 seconds into the problem, the rock has a speed of 0. 1 second into the problem, the rock has a speed of 9.8. 2 seconds into the problem, the rock has a speed of twice this amount. 2 seconds into the problem, it'll have a speed of 19.6. So that's what that acceleration means. Everything that's dropped is going to change speed by 9.8 meters per second squared. So the equation to solve it with will be our favorite. So I replaced the x with a y just to represent that it's going in the vertical direction. And I'll plug everything else in. When I plug it in, it'll be negative 80 equals 0 times time plus 1/2 times negative 9.8 times t squared. So fortunately, because of this 0, the t cancels out, so we don't have to use the quadratic equation. Our next line down will be negative 80 equals, I have to multiply these two numbers together. I have to multiply 1/2 and 9.8. This is a good number to memorize. You don't have to memorize it, but just remember that 1/2 times 9.8 is negative 19.6. That is totally wrong. It's going to be negative 4.9. So go ahead and memorize that. I was thinking 2 times 9.8 is 19.6, but this is 1/2 9.8. That number is going to pop up a lot. From here, I divide both sides by 4.9, negative 4.9 to be specific. Those will cancel out. So I'm left with 16.3 equals t squared. And finally, to undo the square at the top of the t, I will square root both sides. So here's our answer. T equals 4.04 seconds. For my math geniuses out there, you have to keep in mind this is actually plus minus for both of the square roots. I'll just put it on this one. For the square root, it's plus minus, but you can't have a negative time, so we just put positive 4.04 seconds. Okay, we're going to fly through one more example just to give you an idea of what else we can see in these types of problems. And that will be example 2. I'm going to scroll up for a second in case anyone needs to see that part. If you don't get it, ask the person around you. And now stop. We have to do example 2. Here's example 2. A baseball is thrown straight up with a speed of 20 meters per second. How high will the baseball go? A baseball is thrown straight up with a speed of 20 meters per second. How high will it go. So this is going to be very similar, just going to be a little bit backwards. Instead of dropping it from a velocity of 0, we're throwing it up until it slows down and stops. That's what happens when you throw something straight up. You throw it all the way up, like this. It slows down, until it gets to its highest point, and then it'll turn around from here. So we got to label this a little more particularly. This will be y initial. It has an upward velocity in the beginning of 20 meters per second. It slows down until we get to our final height, and that will label our displacement. The displacement that will label the change in y that we see in our equations. Let's see. Okay, so we want to know that change in y. That's what it's asking us of. We want to know change in y. They said that it has a starting speed of 20 meters per second, so that's at this location. At y initial, we have a speed of 20 meters per second, so that means v initial is 20 meters per second. It slows down until it reaches a final speed of 0 meters per second, and the last thing that we know is that a is negative 9.8 meters per second squared. So everywhere on Earth, your y acceleration is going to be negative 9.8 meters per second squared. If we were on the moon or something, we would have a different acceleration. Every planet has its own acceleration. Saturn is roughly 11 meters per second squared. Mars is a lot less, 3 or 4 meters per second squared, I'm guessing there. The moon is around 1.2 meters per second squared, but anywhere on Earth, we're going to use negative 9.8 meters per second squared. Gotta memorize that, fella. So the only equation that we can solve in this case will be, I think it was called number 4. Bf squared equals v initial squared plus 2a. And instead of writing change in x, I'm going to take that same old equation I had and write change in y, because it's going up and down. Plug everything in from there. When I plug all the numbers in, I'll have 0 squared equals 20 squared plus 2 times negative 9.8 times change in y. So the next line down, you'll see the mistake I made earlier pops up in this problem. 0 equals 400 plus negative 19.6 change in y. So there it is. That's what I was trying to do before, but I made a mistake. To solve, we'll subtract 400 from both sides. Getting a little messy here. Put a line so I don't mix stuff up. So we'll have negative 400 equals negative 19.6 change in y. And the last thing I've got to do is divide both sides by negative 19.6. Which gives us an answer. Change in y equals 20.4 meters. Bam. And that makes sense. This displacement is positive because we move up. If you wanted to be really specific about this problem, like that answer's fine. It's the right answer, but it's not quite labeled correctly. Triangle y doesn't tell us a height, it tells us our change in position. So if you wanted to be specific, you could expand this part out a little bit. Change in y means y final minus y initial, and that is equal to 20.4. Technically, our initial position, our initial y, is 0 because we started on the ground. Y final minus 0 equals 20.4. So you could write it like this if you are very, very particular. y final tells us a height, it tells us a position. So that's about it. We solve these kinematic equations just like we did before, but since they're in free fall, we use negative 9.8 for our acceleration. Thanks very much. See you next time.